Hey everybody. So we're gonna pick up on where we left off with problem 5. So as far as we had gotten our governing equations for the backwork ratio and the thermal efficiency. The only thing that we have left to do is go through and fix each one of our states. So tired of writing in black ink, so let's change it to blue, something more friendly. All right. So state 1. The only thing we really need are the temperatures, and that's given to me, so I'm good. That's 300 Kelvin. And state 2, so this is after that isentropic compression process. I'm given what the pressure ratio is. Pressure ratio is 3. I'm also told that the isentropic efficiency of all the compressors and the turbines, they're all 100%, so I don't have to figure out, what is T2S and then T2. Well, T2S is T2, so write this just as T2, which is, like I said, it's T2S. This is equal to 2 over P1, K minus 1, K. So K is equal to 1.4. Our pressure ratio is 3, and as long as everything is in absolute temperature units, I get a temperature T2 of 410.63. Right. So I'll kind of actually feel like I need to highlight some stuff, make it look nice. There we go. All right, so now we're at state 3. In state 3, notice is given to you, so you're all good there. T3 is the same as T1. It's 300 Kelvin. Go. All right, so now we're on to T4, and super exciting, because what we'll find is that because the inlet conditions for that second compressor are the same as the compressor for the first compressor, so the inlet conditions are the same for that compressor, for each of those compressors, and then the operating conditions are the same, right? It's the same pressure ratio, it's the same isentropic efficiency. And so what you'll find is that T4 and T2 are exactly the same, but you can, if you wouldn't automatically jump to that conclusion, that's okay. Plug it in and you would arrive at that same conclusion. But it's because, like I said, it's because the operating conditions and the inlet conditions are exactly the same. It's, like I said, it's the same as for T2, 410.63 Kelvin. Right, perfect. So it's like we're on to state 5. So state 5, perfect, that's given to us. So this one's actually pretty, shaping up to be pretty darn easy. As T5 is given to us. 1200 Kelvin. Perfect. Highlight him just because. And then we've got state 6. Easy peasy. Right, so if we look at our diagram here from 5 to 6, we've got, ideally it's an isentropic expansion process, and it is an ideal case because we have an isentropic efficiency of 1. So our T6, we have an isentropic relationship applied for the ideal gas, and we're using the isentropic relationship. Let me switch that so it's 7 over 6. I'm sorry, 6 over 5. Oopsies, got ahead of myself. but it's a isentropic relationship for an ideal gas with constant specific heats. P6, P5, that's 1 over 3 to the K minus 1 over K. And I've got a T6 value of 876.72. I'll highlight him. And same kind of idea as what we saw with that second compressor there. Got same inlet conditions for the second turbine and the same operating conditions. And so when we apply our isentropic relationship for that second turbine, I haven't forgotten state 7, I'm just kind of getting ahead of myself. But when we apply our isentropic relationship for that second turbine, what we'll see is that our outlet condition is the same. In other words, our T8 is going to be equal to T6. Okay. Of course, our T7 is the same as T5 that's given to us. Okay. All right. And so at this point, I've got everything that I need. I've got all my temperatures, and so if I plug all of that in, I get a back work ratio of 0.342 for 34.2%, and then I get a thermal efficiency of 38.2%. Perfect. So, and kind of highlight it as well. Okay. Righty. So, got the next one. So air enters the compressor of a regenerative, so regenerative meaning there's a regenerator there, cold air standard meaning that we have constant specific heats. So cold air Brayton cycle with a volumetric flow, that's V dot, volumetric flow of 60 meters cubed per second, and at 8 bar or 0.8 bar and 280 Kelvin. Pressure ratio P2 over P1 is 20. The turbine, the maximum temperature in the cycle is 2100. And you'll see they didn't actually say, like, that's after that combustion process, but it stands to reason that the temperature is going to be highest for that combustion process. And so it would be up to you to know that this heat exchanger right here, that is, and I'm going to put it as Q dot, that guy right there is how you're modeling that combustion process. And so the highest possible temperature, right? If you follow from 1 to 2 to 2 to 3, 3 to 4. So 1 to 2, pressure's going up, temperature's going up. From 2 to 3, you've got regeneration where you're recapturing some of that heat that would have been lost. Temperature's going up a little bit more. 3 to 4, you're modeling that combustion process, right? Constant pressure heat addition process, temperature going up a little bit more. And then from 4 to 5, and it's an expansion process. So the pressure goes down, the temperature goes down. Then from 5 to 6, you're transferring some of that waste energy back into the cycle. Whoop, goes down a little bit more. And then from 6 to 1, it's not drawn. However, do keep in mind that, yes, that's an exhaust process, but you're modeling that exhaust process as a constant pressure heat rejection process. So it's not a real heat exchanger, but it's just how we're modeling that exhaust process. So that's our Q dot out. And then while I'm at it, I might as well put this W dot in and then a W dot out here. And I think that's good. And you'll notice that I haven't put I could make a note that yes, there's, if I kind of zoomed in here, yes, there's some heat being transferred from this little squiggly to that little squiggly. I could call that Q dot regen, or just, you know, it's M dot times gen. But the reason I'm not making a big, huge deal about it is because it's not going to go into the equation for the calculation of that thermal efficiency or anything like that. All right, and of course unfortunately, I've got some isentropic efficiencies that are less than 1. All right, and then I'm supposed to find some stuff. So W.net out in megawatts, the thermal efficiency, and then the Q.in probably in megawatts as well. So, what's my solution here? So first things first, I want to get my governing equations. And then once I get all that, then I'll go through and I'll solve for each one of my states and figure out what I need to do. So for the W.net out, and I'm going to note him in green. So W.net out, he's equal to any W.out minus any W.in. Of course, I could put him in terms of, I could say, well, W.net out is equal to Q.net in. That would be okay too. But I'm going to keep it like this because it's not really going to save me any work. Okay. And then this is going to be, well, might as well put this in terms of little w. This will be little out minus little work in. And so now I got a little bit of some thinking to do here. And what I'm going to do as well, kind of take a step back. And up at the top here, I don't know if I've done a great job of kind of getting that first law, showing how that first law breaks down. So your first law for an open system, EDT equals Q dot, or it's Q dot in minus Q dot out minus W dot out minus W dot in plus sum of the M dots times the enthalpy plus the kinetic energy plus the potential energy minus the same thing going out. This is going to be applied for any section of that cycle that we might want to look at. And there are some things that are going to go away, right? For the entire cycle, we're all of these cycles that we're looking at, we're assuming they operate at steady state. And then for all of these cycles that we're looking at, we're going to say the kinetic and potential energy changes are equal to one another. And then one thing that you'll notice is that, well, let's actually keep on with this. So that would give me, if I keep on going here, there'd be a Q dot in, it's Q dot out, minus W dot out, minus W dot in, and then it would be, if I bring things over to the other side of that equal sign, it's going to be the outlet minus the inlet. M dot H at the outlet minus M dot H at the inlet. And for a one inlet, one outlet control volume, I'm going to divide through by that M dot. Actually, it doesn't even matter. Doesn't even matter. Doesn't even matter if it's a same thing. So if you look at this whole thing, it doesn't matter where where I'm defining that m dot. So m dot, it's the same at state 1 as it is at state 2, it is at state 3, as it is at state 4, 5, and 6. So I'm going to divide both sides by m dot, because it won't matter what control volume I'm looking at. It's the same m dot through the whole thing. And so what I'm going to get for my first law for an open system, if I assume steady state, no changes in kinetic and potential energy changes, and then also because I've got just one continuous loop, nothing's like splitting up, got one continuous loop, this is going to give me q in, little q in minus little q out minus little work out minus little work in equals sum of the m dot h's going out minus the sum of the m dot h's going in. Okay. So that's my first law that I'm working from. And so the workout. So if I applied that my first law, so I'm looking to define this part. Let's see. So that little w would be what? Be, if I looked at my first law over here, that work out. Well, I don't have any Q in or Q out or work in. It's a workout process. And so you can see the negative there. It's going to be the inlet minus the outlet. So it'll be H4 minus H5. And of course, we could put this in terms of CP delta T, and we're going to do that in just a second. And then the little work in, this guy right here. So if I'm looking at him, it's going to be, well, when I apply my first law, have any Q in, I don't have any Q out. It's not a work out, it's a work in. So that you got the two negatives that cancel out there, and it's going to be the stuff going out minus the stuff going in. So let's do that. Stuff going out, H2, minus the stuff going in. Perfect. Like I said, this is going to be CP delta T, T4 minus T5, because I'm assuming constant specific heats. Right. And now the only other thing that I need is, of course, my mass flow rate. And so I think, I don't know. So this guy right here. So remember, he's the same no matter where I look in the cycle. However, the thing that is going to give me some information about the rate at which things are flowing is this guy. So I think that's kind of where I'm going to start. This guy, m dot, doesn't matter where I look, I'm going to define him at state 1, but it doesn't really matter. It's the same wherever I look. So this is v dot 1 over the specific volume at 1. And remember, I have an ideal gas. And so that specific volume will be calculated using my ideal gas law. And so I think actually I've got enough information to sort of plug that stuff in. So R is the specific gas constant for air. So R is the R bar, which is the universal gas constant, over the molar mass, which for air is 28.97 kilograms per kilomole. But I know for air that R and SI units is 0.287. That's what it works out to be. 0.287, and it's kilojoules per kilogram K. And then my T1 is 280. Erase this just so I've got a little bit of room. And then I'm going to bring the pressure up to the numerator just because. So dot is 60 meters cubed per second. And like I said, I'm going to bring that pressure up. Now, you may or may not recall, if you want your units to work out correctly, put that pressure in kilopascals and it will work out. So 0.8 bar is really 80 kilopascals, and the reason that it works out, I'll show you right now the unit conversions. So a kilopascal is a kilonewton squared, and a kilonewton meter, I should say, is a joule. So I think that will make my units work out. So I got kilopascal, pascal, and then for my meters cancel out. Kilonewton, kilojoule, kilojoule, Kelvin, Kelvin. So if I'm not mistaken, the only thing I've got left is the kilograms per second. So that on there. See if I've actually got that. Be sweet if I did, but I apparently do not. That's okay. So let me get my throw some stuff in here now that I've got it. So 60 times 80. Looks like I've got 59.73. That sounds good to you too. So 59.7, and that's kilograms per second. Let me double check that the units. So 60. Yep, that looks okay with me. All right. And so I'm just gonna sort of bring all of this together now. So my W dot net out is equal to my M dot times CP times, let's see, so I'll have T4 minus T5 minus T2 minus T1. Perfect. And so, this is going to be, well, just start plugging stuff in. So this is 59.73 kilograms per second. My CP with a K value of 1.4, that CP is 1.005, and that's kilojoules per kilogram K. And then of course I've got my temperature. So T4, already got him, don't I? 2100 Kelvin minus T5, which I don't have, minus T2 minus T1, which I need that, or I've got that. So it looks like really I just need T2 and T5 at this point. Perfect. So I'm good there. So that's part A. Part B will of course be my thermal efficiency. So I can put him in terms of W dot net out and Q dot in. I've got to calculate Q dot in anyway, or I could put it in terms of Q dot out and Q dot in. It really doesn't matter, I guess. maybe I'll make things a little bit easier on myself and actually just put it in terms of w.net out and .in. And remember I said that the mass flow rate, it's the same throughout this whole thing. So you could divide the top and the bottom of that equation by m dot and not change the value of that ratio. And so this just becomes little w net out over little un. And so I've got the equation for that top one. In fact, I'm just going to leave it as CP. I'll leave it in terms of the temperatures. So T4 minus T5, T2 minus T1. Perfect. I think I want that smaller. And then I'll have a CP delta T for the QN. So if I apply my first law to this little guy right there, if I apply my first law, that's going to be, well, it's a Q in, not a Q out. Don't have any work in or work out, and so it's going to give me the stuff going out minus the stuff going in. So H going in, H going out, H4, oh, and I'm going to erase this in a second, but H4 minus H3, but I could put that in terms of CP delta T, which I'm going to do right now. So it wouldn't be CP times delta H, it would be CP delta T. So that's going to be T4 minus T3. All right, perfect. And so at this point, I think I'm good. I really, so I'll need to solve for all the states, with the exception of state 6. So state 6 is sort of an optional. I said, I can figure out based on this equation right here and get q dot m. It's just going to be the thermal efficiency times this guy. And I'll put a little note. So I want to find T6. It's optional. And it might be good if you have time. Because you can check your numbers. Is your w.net out equal to your q.net in? Okay. Or, it's a little w, right? It has to be that way for it to be, for any thermodynamic cycle, that's what has to be true. So it's optional, but it's not necessary for this problem. Okie dokie. So let's go through and solve for each of our states, and yeah, that should do it. So state 1, we know. State 1's given to us. So T1 in 80 Kelvin. State 2, unfortunately, we have a isentropic efficiency of less than 1. We have 92%, so I do have to figure out, use my isentropic efficiency to get state 2 T2s, and then from there I'll get the actual T2. Right. My T2s, I've got 658.99. Kelvin. And I feel like I should highlight these. That's going in there. But that T2S is not, right? But I do need the state 2. So isentropic efficiency of the first compressor is 92%. This is the ratio of the two works. The bigger number has to be on the bottom so you can reason out, well, for a compression process, ideally you put a lot less work into it. So that's going to be the smaller one. So it's going to be CP, T2S minus T2, or T2S minus T1, I'm sorry, over CP times T2 minus T1. So from there we can get our T2, and I got a T2 of 699.7. So that's the number I'm going to be plugging into that equation. State 3, let's see what I know about him. I have to go back up to my diagram here. So state 3 is right after that regenerator, so it's after the regeneration process. And so we had a similar problem with a regenerator last time. And what we did is we just kind of had a placeholder. So I know my regenerator effectiveness, it's 85%, so 0.85. And it's defined as that Q regen over gen max. So that Q regen, if I define it from the bottom squiggly, I defined it for this little squiggly right here. Well, that Q regen ends up being, it's a QN to that kind of orangish squiggly. So if I applied my first law, it would be the sum of the H's going somebody's probably like has been sitting there for 20 minutes like, come on. These M dots don't need to be there. Sorry for whoever has been like, oh, annoying. Every now and then my software doesn't like me. Like I click on a spot that's not supposed to be there, or that it doesn't like me clicking on. Sorry, this is H's. There's no M dots in there because I divided through by M dots. So somebody's going crazy, and finally I've cleared things up. So sorry about that. All right. Yeah, this is a problem, I guess, with asynchronous. Nobody can yell at me when I make a stupid mistake like that, but hopefully you realized what I did, because yeah. All right. So our Q regen, so it's going to be the out minus the in, so 3 minus 2. So, and I'm going to go ahead and put it in terms of CP delta T. So T3 minus T2. And then the regen max would be the heat transferred into that yellow line. If by the time your working fluid traveled from state 2 to state 3, it would have heated all the way up to the same temperature as T5. So instead of being, you could think of this as T3 prime, but really it's T3 prime, which is the same as T5. Okay, so I don't know T5 yet, so I kind of can't do anything about that now, but I could solve this. This would be the regenerator effectiveness times T5 minus T2 plus T2. All right, so whatever that is, and we'll come back to him shortly. Almost done. All right, state 4, this was the maximum temperature in our cycle, which we reasoned out would be after the addition of the heat for the combustion process. It's 2100 Kelvin. That's our T4, 2400. I'm sorry, not 24. 1. Yeah. 100. Kelvin. And then from 4 to 5, we have the expansion within the turbine. Ideally, it occurs isentropically, but we do have an isentropic efficiency of 95%, which relates those two works, right? The ideal case is going to be on the bottom because ideally for a turbine, you get a lot of work out of it. All right, so this T5S 4, 5 over P4 to the K minus 1 over K. And so one thing let's see, go look. I need to figure out, do I know P5 over P4? Is that given to me? And it's not specifically, but I can look at where my pressures are equal to one another. So, one of the things about an ideal cycle is there's no pressure drops where you don't want it to occur. So across the piping from state 2, state 3, state 4, and then same thing over here, state 5 to state 6, all the way back to state 1. And so, my pressure ratio P5 over P4 would be 1 over 20. So I'm going to plug that in down here. So my T5S ends up being 892.7. But of course, I'm not going to use that. It's the T5, which I calculate from that isentropic efficiency. Okay. So my T5 ends up being 952, and I realize it's behind my head. 952.66 Kelvin. Here's that one. And I guess we've got enough information to go back and plug things in for T3. And hopefully I've got it right. 913.55 Kelvin is what I've got. And at this point, I think I've got enough. Like I said, if you wanted to calculate that T6, you could. In fact, I'll go ahead and do that just because. So if you wanted to get T6, you've got two options. You could use that regenerator effectiveness equation. So it's still Q regen over Q regen max, except you're defining it not with that bottom sort of squiggly there, but the top squiggly, this guy. So that Q regen, that small little squiggly arrow, it's going out. And so when you apply your first law to it, all you'd have, that Q regen would be a Q out. And so it's going to be the in minus out, 5 minus 6. So H5 minus H6, or I'm just going to go ahead and write it up here just so. So this is H5 minus H6, or CP, T5 minus T6. All right, and then on the bottom there, it's the regen max. So it would be, okay, I'm coming in at state 5, and if I were able to get the maximum amount of heat transfer, then I would have lowered my temperature to the lowest possible temperature at state 6 that it could be, and that's going to be the inlet temperature here. So this is going to be T2 minus 5 minus T2, sorry. So T5 minus T6 over T5 minus T2. So 5 minus 6, 5 minus 2. Okay. All right, and so if I did that, I would get a T6 of 731.05 Kelvin. Option 2 is you could do an energy balance around the regenerator. Right, so you've got, so this is 5, 6, that's 2, that's 3. And so, this entire regenerator, it's a heat exchanger. And so the whole thing's going to be insulated so that you only have heat transfer between those streams there. And so when you apply your energy balance, you're going to have the sum of the m dot h's going in is equal to the sum of the m dot h's going out. And of course, your m dots are the same, so you could divide through, and you'd have the h's going in, H3 plus H in, H2 plus H5, then going out, H3 plus H6. Put this in terms of CP delta T's, but either way, it's going to be T2 plus T5, CP, T3 plus T6. If it bothers you that it's adding things, make it H2 minus H3 equals H6 minus H5, right? The relationship of that CP delta T, it's still going to apply. And so T6 should be T2 plus T5 minus T3. And you should get the same thing. So you got some options there. Like I said, it's not necessary. And from there, it's just a matter of plugging things in. So I believe what we've got here, this W dot net out ends up being 44,164 kilowatts. We wanted in megawatts, so this is 44.2 megawatts. And then your thermal efficiency ends up being 62%. Of course, this would be whatever 0.62 times 44.2 is. I will highlight those answers. That's it. So right now we're at about 43 minutes, and so I won't add another problem, but that leaves us, I think we've sort of mostly gotten through a lot. So we've got problem 8, problem 9. So we've really just got 2 more problems to do. So that's probably going to get 3 lectures next week. Look ahead again about when your test is. So let's see. Oh, that's actually about perfect. We've got 2 more lectures, so we'll get through most of the rest of the problems probably on Monday, and then we'll finish up whatever we need to on Wednesday, and then we'll have our first exam next Friday. So, alrighty. Well, hopefully that answered everybody's questions. Once again, I'm going to have office hours just for a half hour starting at 2:05. I'll be in there 2:05 to 3:35. So maybe I'll see you there. All right. Thank you.